Hi all, I'm Kunal and I am an AI engineer. So I'm starting my YouTube channel where I would post different things regarding AI, data science, and all the other stuff that is related to AI. So we or you all might be saying a lot of talk about AI, that AI is booming a lot. Things are getting automated, and then even software engineering is going to die, etc., etc. I mean, all these things are correct to some extent, but they are not the facts. I mean, this is a very controversial topic. But to not to delve into this topic right now, but something that does not change is always the fundamentals and the basics. So, what I really feel is that everybody should at least know the fundamentals of how AI actually works and how these things are working. So, even before diving deep into AI agents and how AI systems are built, I want to cover the fundamentals of AI. And when I say the fundamentals of AI, the best thing that always comes to my mind is one Python framework, which is Numpy. So what I'm trying or what I'm planning to do is I will train a neural network using pure NumPy. No deep learning frameworks used like PyTorch or TensorFlow. I mean, of course, PyTorch is again inspired through NumPy. We would have separate talk on that, but currently I'm planning to, make videos on NumPy first, then train a neural network using pure NumPy. It would be an FCNN, a fully connected neural network, and then move on to different topics. So the agenda of today's video would be to discuss even the need of NumPy, like why even NumPy was even needed. So we have lists in Python, we have arrays in Python, and even after having so much of content or so much of tools in Python, why do we even needed NumPy? And for this tutorial or for this understanding, I would use something called as a Jupyter Notebook. So these topics, Jupyter Notebook, Visual Studio Code, or Anaconda or Conda, these are some of the jargons that are related to data science and AI, about which I would make separate videos. And to explain them in very short, so Jupyter Notebook is kind of an environment where you can have like a notebook kind of a thing where you have cells, and in each cell you write Python code, and in that and at a particular given point of time you can run particular cell. So this helps in testing, debugging, and experimenting with AI, understanding how your code is working properly, and helps into debugging a lot. So that is a Jupyter notebook. Now Anaconda or Conda is nothing but it allows you to create uh, different environments which has different Python versions. So maybe I can create a Conda environment which uses Python 3.10, and once the Python version changes, all the other different libraries that you would install in Python would also be depending on that version and how they are stable among their own dependencies and all. So that's what Conda enables you, and Visual Studio Code would be the actual coding ID where all these things would be situated. So Jupyter Notebook or the what do we say, the uh, Conda environments and all. So let's directly deep dive into all these concepts. So okay, so this is the actual notebook that I'm going to use, and this notebook consists of a lot of textual explanations regarding NumPy, understanding NumPy, and in many of the places, what I have always seen is everybody explains different tools and different handy things that are available in NumPy, but what is actually happening behind the hood, or what is that is making NumPy so much popular, And why is it even a thing before PyTorch or TensorFlow? Why was it even a thing before that? It is today as well, but why was it even that much famous, or why, or how did it even change the AI, the entire AI industry? So to start with, first of all, let me just make another notebook where I will just make all the coding and all this stuff. So let me name it as numpy underscore uh, prod maybe dot ipynb. Okay, sorry, I just messed up with it. Let's rename this dot ipynb. Oh, okay, I made folder by mistake. Let's make it a file. Numpy underscore prod dot ipynb. So mm, just a second, let me rename this proper name. Okay, cool. Now what you are seeing here is a notebook or a Jupyter notebook, and for this entire project, let me make a Conda environment. So Conda create. So I just previously tried creating one, so I already have this command. So let's create a new environment called neural nets. So what actually is happening here is I'm telling Conda to create a new environment named neural nets using Python version 3.12. So it's asking for me to proceed, and I will say yes. Let's proceed. Okay, cool. So the Conda environment is created. Now, you can see here in the right corner, there's a thing called a select kernel. So this actually allows, to select different Python environments, or different Conda environments, uh, whichever you have created. So here by default it is routing to neural nets, but if I click on select another kernel, I have an option to select Python environments, and these are the different Conda environments which I can select. But for now, I would select the one that we just now created, which is the neural nets, which is this one. So let's select this, and I would click on this code. So when I click on this code, I have this cell thing coming in up, and now I can start coding in Python. So let's write something called as import numpy as np. So what am I doing here? So here I'm just importing a library called as NumPy, and I'm abbreviating it to NP. Why am I doing this? So this will enable me to, wherever I'm using this word NumPy, I can just use NP in place of this word NumPy. So let's run this cell. For running it, you need to press Shift and Enter. Okay, now it shows me a message that IPY kernel package is not installed. I need to install this. So this is something which is required to run any cells or any Jupyter notebook. So in Visual Studio Code or any place where you're running your Jupyter notebook, if it's not installed, it directly shows you a pop-up that you please install it. So I'll click on install. By the time this thing is getting installed, let's go on to, this thing. Okay. Now I will try to go a bit slower, and I just want one thing from you guys, that please listen to what I'm saying very carefully, because there are a lot of things going on here. So, why was NumPy even required? What was the need of NumPy? We had Python lists, we have arrays in Python, and we had C++. And if I speak about these languages, these are very fast languages as compared to Python. Then why was there a need of NumPy, something like NumPy, in that too in Python? So the thing is, whenever, for example, I am an AI researcher, or not even AI researcher, or I am just a person who need to use a tool or a programming language to write different mathematical equations. So, for example, I want to write a program that will calculate matrix multiplication. Okay, I can do that in C, I can do that in C++. But what is the problem? When I do that in C or when I do that in C++, the amount of lines of code and the complexity that goes into the syntax, and then using different variations in these languages, in these programming languages, is a lot more. So in short, C and C++ also allows this thing, but it's quite a lot more complex as compared to Python. And in order to solve this problem, NumPy was invented. I mean, not only this is one of the problem, but this was also one of the reason that, so if, see, let me tell you from an AI researcher or any, for example, a mathematician or a theoretical physicist point of view, that whenever I want to, try to do anything related to mathematics, my major focus is that how much easy it is for me to, write it down write it down using a programming language, so that I just don't want to focus more on the syntax part. So that's quite energy exhausting thing. So for example, if I'm a mathematician and I'm writing an equation that y is equal to mx plus c, this is an equation of a straight line, and the way I'm writing it on a paper, and I'm habitual of writing it on paper, similarly, how much habitual could I be doing the same thing? I mean, how much is the similarity between writing it on paper and doing it in programming? If this similarity is much more, it becomes very easy for me as a mathematician. So in order to do this, NumPy was one of the thing that was invented, because if you look at Python, it's a very beginner friendly language. So it's like even writing down plain English. Sometimes it feels like that. It's not like that exactly, but it's way much more easier and way much more beginner friendly as compared to any other language. So that is one of the reason. And if you look at this history part, uh, so that's what is being explained here, whatever I explained current just now, that use Python lists, those are extremely slow. So switch to C and Fortran, it's very complex. So this was the reason, or this was a huge gap. And then enters the creators. So in 1995, there was this person called Jim Eugeney who invented or who introduced a framework called as numeric in Python, way much before NumPy was even introduced, for the same reason. Then in early 2000s, Travis Oliphant, he integrated SciPy, NumArray, and this numeric. He merged them all and tried to use them. And finally, in 2006, he introduced or invented NumPy. So, what it actually solved was, how can we make Python as powerful as C for numerical computing without losing simplicity? So, see, C was doing it already. Okay, we had C was doing it already, but we want the simplicity that the Python is providing, right? So for that reason, we want to introduce same thing, same computing power or same computing capabilities into Python, but with similar performance of that of, and that's the reason NumPy came into being. And if you see, NumPy's majority of the backend is written in C and C Python. So that's another discussion point. We would not go into that currently, but yeah, this is the whole picture behind why NumPy was even needed. Okay, now see, these are some set of problems that we have and how NumPy was the solution to all these problems. So let's discuss these problems one by one. Uh, okay, this thing I will directly explain you through the diagrams. That is much better. So let's move on to this diagrams.io thing where I will explain you some of the things and some of the concepts using these diagrams. So let me quickly take a table. Okay, so this is a table and let me enlarge it a bit. Okay, sorry. And let me take this text box. Let me center it. Increase the font size so that it's visible. And consider that this is memory address block uh, ck block in Python. Okay, and there is this number or integer 10 stored at some memory address location. Okay, and let me write a piece of code in Python. Uh, for example, I am writing, let me increase the font size first. Okay, I am writing that there's a variable which is equal to 10, and then there is a variable b which is equal to a. Okay, so so parallelly what we can do is go to VS Code and do this thing. Okay, so this IPY kernel is finally installed, but now we are getting that this module Numpy is not found. So let's install it. So one more thing, whenever you want to run any bash or Linux command, so basically all those commands that you run on this terminal, if you want to run that in Jupyter Notebook, you need to add an exclamatory mark, and after that you can write the same command. So pip install numpy. Okay, cool. And then shift enter to run this cell, and numpy successfully installed. Let's run this cell again, shift enter, and now it shows no errors. Okay, so what were we discussing? Okay, yeah, so let's do the same thing that we did over there. So let's initialize a variable a equal to 10 and a b variable which is again equal to a. Now what actually happens is in the backend is, so let me say this is a, let me increase the size of this to 18. Then let me say that this is b, let me increase the size to 18 again, and this is my b. Okay, sorry, let me align these two, and let's take this curve arrow. Oh, sorry, okay. This is much, way much better. Okay. Similarly for b. Well, this is quite simple to understand. So what is happening here is the a and the b, both of these variables, or both of these variables are pointing to a memory address block where this 10 is stored. And remember one thing, this is the most important thing, that this 10 is a Python object. Remember it. This is a Python object. Okay, and this is fine, this is simple to understand, but something that is interesting is, let me pull this over here, and combining these two, let me write one more variable uh, called as count and equal to 2. So what is this, or what this even mean? So what actually happens is, for an integer specifically, or specifically we are speaking about integers at this place. So whenever I do something like this, so what Python internally does is it it maintains the count of number of variables that are pointing to some Python object inside a memory address block. So basically, these two variables are pointing to the same memory address, and Python internally maintains that how many variables, in this case only two variables, are pointing to this memory address block. And this count is called as a reference count. Okay, now in this case, it's A and B, and if I go to my VS Code and for example I write something like this, that my underscore list is equal to 1 comma 2 comma 3 comma 4 comma 10, and should I write that now? Yeah, I can. So let's uh, loop through this list, maybe my list, and then print the type of each of this integer, and after doing that finally print the type of the list. So let's try to run this piece of code. Okay, cool. So you can see this all these five are of class int, and then this is finally, this list is like, this list is class list. And why am I doing this? Try to understand what is happening here. When I'm declaring this numpy list, not numpy list, sorry to use that word. When I'm declaring this list, pure Python list, these each specific elements are treated as individual Python objects. They are not pure numbers like we have in C and C++. So if I say, or if I declare an array of numbers in C or C++, how C++ treats it is, for example, this is a int32 integer. So basically, it's pure int32 integer. It's not a Python object. Python object, or it's not a C or C++ object. C or C++ would treat it as an integer 32. So basically, it would be 4 bytes, each byte of 8 bits. So 8 into 4, 32 bits. Okay, so this is how C works. But in Python, this individual element is a Python object. It's not pure scalar or pure integer. Try to understand this point. It's extremely important. Now, what was I trying to say? Okay, yeah. So let's introduce one more thing here called as my list. Okay, increase the size 18, and let's write this as my underscore list. Now what we are doing is, again, this my underscore list is also pointing to this address. And why is it doing this? Because we have declared it as one of the element of this. So it would also be pointing to 1, 2, 3, 4, but for now, because we have a equal to 10, b equals to 10, and something like this, then in that case, or for that reason, we would just look at this 10 Python object and not the other ones. So if I go here, now what will happen is this thing would also include this, and this counter would change. Are you getting this? And let's move it to the center. Okay. So this is something that actually happens in Python. And for example, one more thing to add in here is, if I uh, mm, make a function, maybe what can I do? with a number. So let's mul multiply. Okay. So if I pass an integer to this and I return x into 2, and then if I write multiply 10, and let's see what we get. We get 20, so it got multiplied by 20. Now in this case, this x, so let's introduce one more thing in here. This is an x variable. Okay. 18, and then again the same thing. Let's increase this, and here the counter would go to 4. I think you guys have understood what is actually happening. So the number of times I am using 10 and storing it to some integer or in any of the Python object, this count would keep on increasing. So internally, Python is actually maintaining the number of variables or the number of Python objects that are pointing to this 10, which in itself is another Python object. Try to understand this. So this is what is happening. Now let me give you one more interesting thing. So now if I'm writing here a is equal to 20 and I executed this. Okay, so if you remember, we declared a to be 10 over here. Now what would happen is this reference of a to 10 would actually not, let's not delete this. Let's write 20, where it should, it would be easy. Let's write it over itself, here itself. So now a is not pointing here, but a is pointing to this memory location. Okay, and this would squeeze into this 3 itself, to this 3 things itself, and let's move this here, and this count value would decrease to 3. So I think you understood what is the thing. And now what is something that is more important is you just remember this part. This thing is okay, that what is referencing to what and what is not referencing to what. This is fine. But what this actually mean is this is another integer that Python is itself maintaining for this single Python object, or maybe for every single Python object that exists. And when it is maintaining an integer, it's an 8 bytes of integer. Each byte 8 bits. 8 into 8, 64 bits. So it's adding 64 bits of more, it requires for this single integer requires 8 bytes for the reference pointer to store. This is one thing. Okay, so if you go here and if I come here, so that is the same thing that is being explained in this reference count, which is a 8 bytes integer. And the same example is given that if it's a equals to 10 and etc. And then so why is it making it over here even slower? So this reference count is acting as an overhead, right? Because normally if I say I have a 32-bit integer, it's 32 bits. That's it. 32 bits is 4 bytes. In 4 bytes, I'm storing the entire integer. But here 8 bytes itself are been taken off for maintaining the count, or for maintaining the reference count. So it's actually an overhead. So whenever I want to do any operation on that, it's going to have many memory switches inside the memory block address, and that's going to cost us a lot. So you assign a variable, pass it to a function, or store in a list. It would always increase or decrease the number, or what we can say, the counter value. So you assign it to a variable, increase, pass it to a function, increase, store it in a list, increase. So Python must increase reference count or decrease reference count, and this adds an overhead. NumPy avoids this for individual elements. So NumPy stores it. A NumPy array would store an integer similarly, in a similar way in which they are stored in C and C++. It stores it in contiguous blocks of memory. So we would come to that later on. So this is one of the problem. Uh, I explained you what is the increase and decrease reference counter actually mean. So here again, there's an example that if a is equal to 10, what happens internally? Python creates an integer object 10. It's an integer object. A points to it, reference count increase to 1. Now when I do b equals to a, what happens? B now also points to the same integer object. Python increases the reference count to 2, and it is a real CPU instruction. So now what does this CPU instruction is? If you guys, I just don't know what that actually used to be the assembly language. So we used to have the instructions. So there's an assembly language that uses instructions set to load data from register, do various operations on the memory blocks, and these kind of things. And even if you want to give any instruction to a CPU, you also do that using that itself. So it's really a CPU instruction to load the object, modify its reference field, and write back to memory. This is happening at the register level, at the memory level. So again, here it's explaining when you store it in a list, what happens? The list stores a pointer to the integer object. Again, the reference count increases because now list also owns that object. Reference count increases again. So that list also has that object, a Python object, which is an integer object. It would again increase the reference count for that Python object, okay, which is an integer object. Passing it to a function would also do the same thing. How it decreases also is discussed. Why is this expensive? Yeah, so this is the real thing. Are you getting it? So now imagine this loop. Now for when I'm looping this, literally what I'm so in this let me explain you this thing. So let's write a number n which is equal to 1 underscore 000 underscore 000, and let's do a for loop for and let's first of all declare a list, empty, or can write my underscore list underscore 1 is equal to, this is an empty list. So for I in range of n, what I would do is my underscore list underscore 1 is equal to, sorry, dot append this I. Okay, so what I'm doing here is I'm looping. So even let me even explain this. This is nothing but 1 million. This is 1 million, and so these underscores are just a way of writing. And what do we say? Python treats this as 1 million. So 1, 2, 3, 1, 2, 3. That's it. What I'm doing here is I'm declaring this number or to 1 million, this variable. and I'm declaring an empty list, and I'm going from 0 to uh, not exactly 1 million, a number before that, uh, and appending it to a list. So now in memory address, I would have 0, 1, 2, 3, 4, 5, 6, 7, up to a number which is 1 less than million stored in the memory address block. And when I do this append operation, because each of these is a integer object, it would have separate counter reference counter for each of the Python object. So don't think of it like count would be count reference count would be equal to 1 million. It's not like that. For each of the what do we say, Python object, in Python integer object, which would be 0, 1, 2, 3 up to million, 1 less than a million, it would create its own reference count for each of them. Okay, so you would, for example, you can think of it as there would be 1 million reference counts for each of these 1 million, what do we say, Python integer objects. And just imagine the memory cost, the CPU cost, CPU processing that would be required to, store these integers, because these are 8 bytes of integers. This is 64 bits. So it's a lot. It's actually adding an overhead. So this is the very first problem. And yeah, that's what it create integer object, increases reference count, store pointer, possibly decrease later, depending how it happens. That millions of memory updates, because those are million numbers. These are memory writes, not cache friendly, not vectorized, not parallelized. These concepts we would come up ahead. So vectorization is again a concept, not parallelized, because these memory operations are not happening in parallel, or there is no parallelization involved, no caching involved, and just memory writing, simple memory writing. Again, adding a overhead. Now, how does NumPy even addresses this? Now, let me tell you the biggest and the most nicest thing about NumPy. Uh, so, let me define an array in NumPy. So, let's write a NumPy underscore array equal to p dot array, and let's define an array 1, comma 2, comma 3, comma 4. So, and print it, then you would see it as a NumPy array. If you want to convert it to list, you will have to do the type conversion. But for now, let's understand what this actually means. Now, what NumPy internally does is, I also explained it previously, that it would store these integers in the contiguous memory blocks. So there would be a starting address of the memory block. From there, each of these, for example, okay, also let me define the data type of this. Data type is equal to np dot int 32. So I am declaring them as 32 bits integers. So each of the integer is 4 bytes. So in this curve, so 4 into how much are these? 1, 2, 3, 4. 4 fours are 6. 4 fours are 16 bytes. So this, there would be a start pointer, and from that start up to 16 bits, 16 bytes of memory, these numbers would be stored. And try to understand, in this individual element is not treated as a Python object. This is not a Python object. If it's not a Python object, it would not have any reference pointer. Try to understand this. So there are 4 things associated with each and every Python object that exists. One of them is reference pointer. which we have discussed. The other three we are about to discuss. But try to understand when it's not a Python object, there is no reference pointer associated with it or reference count associated with it. Okay, so this is just single Python object, which is a NumPy array. So this NumPy array in itself is just one single, what do we say? This NumPy array is just one single uh, Python object. These 1, 2, 3 are not Python object. They are pure 32 bits integers. That's it. And so this is much similar, or this is exactly similar rather, to what we have in C and C++. Okay, so you can see the same explanation. The array is one Python object. The element inside are not Python objects. They are raw C integers in a contiguous memory block. Got it? So instead of pointer, Python object, reference count, so this is how it is in lists. We get this is raw memory. That's it. So 4 4 into 4, if I'm writing it to be a 32 bits, 4 into 4, 16 bytes. 16 bytes of memory is been taken by the entire array, and I'm storing the entire array in only 16 bytes. Here, but in the list, the only one element of it, if it's an integer element, the only one element of it which has reference count of 8 bytes itself. So the 8 bytes are even, I mean, this much amount of memory is allocated only to maintain a reference count. Whereas in this, in 16 bytes, so double the memory of for single whatever is required to store a reference count of single Python object. In the double of that, the entire what do we say list or the NumPy array is stored. So can you even imagine how much is the efficiency or in the memory that is being allocated? So this is why it's so expensive to use lists, especially for mathematical calculations, and that too, which are involved in AI. So it involves a lot of different matrix multiplications, and there are a lot of advanced mathematical calculations included. So this is actually adding an overhead. Okay. So why is this a big deal? Now in Python list operations, we have pointer dereference. So the same thing that as associating a pointer to this, what do we say when you declare a variable, associating a pointer to the memory address of that Python object. So this is nothing but pointer dereference. Type lookup. So type lookup is the next one. We would go to that thing. But in each and reference ref count manipulation, again the same thing that the reference counter increases, decreases. It has to maintain a different integer for that. And in NumPy, we have direct memory offset because you just need to know the start address, and then there are the row strides and column strides. We would discuss all this ahead. What does that actually mean? No object lookup, you don't have to look up to the object, and no reference adjustment. So basically, you just don't have to maintain reference counters for each of the elements in the array, whether to decrease it, to increase it, or whatever operation that needs to be done inside the memory. So when you do this, NumPy loops in C, works on raw memory, no Python object involved per element. So when you are doing this in inside list, it's element to element basically. This is simpler, but if I have to uh, do it in lists, it's element to element, and which is again costing us a lot of memory. Okay, so what is the final dip inside that Python integers are managed objects with lifecycle tracking? So basically, of course, so think about it that I have a list. I have different elements inside that list, and for each element, I am maintaining a reference counter. So it and I am increasing it or decreasing it depending upon how many variables are actually pointing to it. So kind of maintaining a life cycle for each of the element inside an array, isn't it? So that's what it's saying, that managed objects with life cycle tracking. NumPy integers are plain data with no life. So NumPy we just don't need any life cycle because we don't maintain any reference tracking. So all these things, whatever are being said, the best explanation is this thing. Just remember this much part, and this is what is the complete thing about reference counter and how do they actually, work. Now, ultimately, this is the thing. Now, the second thing that comes into picture is the type pointer. Now, what is a type pointer? So, uh, let me just tell you. Okay, so here I printed the type of each of these elements, and then finally I printed the type of the list. So now these types, whatever these types are, so it's a class integer, type is a class integer, and then class list. For each of these element, because it's a Python object, it would have an 8 bytes of memory, or 8 bytes of located memory to point to the type object class. So this is a type object class. For this element it's integer, like for all elements it's integer, and for my list it's a list. So just to point to the type of the object of that Python object, we have 8 bits differently located. So the same thing is what is being explained here. So if I have phi x equals to phi, and this object contains pointer to int, and which is internally represented as phi long type. So it would have a pointer to int. So int in itself is a class, is a type class. So what type of the Python object is this? And then we also have a separate pointer to that, which is a 8 bytes pointer, that is type pointer. And why does Python need this? Because Python is dynamically typed. So whenever run that in an interpreter, uh, on the basis of this type pointer, it understands that okay, this is an integer, this is a string, this is something that is not a float, and so on. Does not have fixed type. The object itself carries its type information. So what does type pointer allow, and why does it even is required? So method resolution. So you can actually understand the different methods. So we call these methods as magic methods. And then what these basically mean is, like when I do, for example, a plus B, whatever is the definition of this plus, like addition, it uh, is something that is being explained by these magic methods. Then operator overloading. So operator overloading is something that allows you to change the definition of this. So for example, I have this function x dot underscore underscore add underscore underscore. The operator overloading will allow you to actually change the definition of this add. Dynamic dispatch, not necessary to understand. Runtime checking, so that's what I explained, that it would check at the time of runtime what type class is it pointing to. Okay, so every object in Python has this pointer, of course. So let me try to make you understand this thing. So we declared an array here, and we have 5 integers inside it. Each of these would have a reference count. Second, type pointer. So these are two. Each of them 8 bytes. Total how much? 16 bytes. So till now we are seeing these two. We have seen these two things: type pointer and the reference counter. So for all of them we have this type pointer. And why 8 bytes? Because it stores a memory address to the type object. Understood. Why is it 8 bytes? Because it stores, or when I say that it is pointing to the integer class or to a float class or to a string class, it is storing the address of it wherever it is located. So address, again, it's an 8 bytes of thing, which is 64 bits. That is why 8 bytes allocated to this. Now comes the third thing, which again acts as an offset, is size field. Now let me tell you one thing, that Python is not like C and C++. So when I say this, in Python, in C and C++, there is a concept of buffer overflow. So if I declare any integer, which is a 32 bits integer or a 64 bits integer, there is a range of maximum and minimum integers that you can, declare. And if you go beyond the max or below the minimum, then it throws buffer overflow. Same like for a 32 bits int or a 64 bits int. But in Python, there is a flexibility, or there is a, what do we say? There is a dynamic way in which it allows you to even declare integers which are higher in number. So what it does, it actually stores an integer in a block of 30 bits. Yeah. So for example, I have 30 bits. I would store a number in 30 bits, and then if the number is exceeding these 30 bits, then I would again allocate more 30 bits, and it keeps on doing this thing. So let's look what I'm trying to say here is, so for example, so then let's rotate this again one more time. Yeah. So for example, this is my first 30 bits block. So for smaller integers, you would have this 30 bits block itself. The smaller integers would suffice in this 30 blocks, 30 bits block. But if there's a larger integer, then it would allocate more 30 blocks to it. Okay. And this thing goes on. So if I declare an integer or a number which is not getting fixed into this 30 block, it would dynamically increase the number of blocks and would allow you to store the number. This is how Python works, and this size field which is being declared here, what it does is it stores the number of these blocks. So maybe again, let's copy this itself and write a text over here. Let's increase the size of this to 18. Yeah, I forgot to even increase the size of this. Yeah, it's again 18. See. So the size underscore field would be equal to 2 in this case. So it counts how many such blocks are existing for that given Python object. Are you getting it? So similarly, that's what it's in, explaining here. And because again, it's an integer, it would require 8 bytes more. So 8 bytes for reference counter, 8 bytes for type pointer, 8 bytes for the size field. So 8 3 are 24 bytes. Try to understand. We are using up till now we have used 24 bytes to allocate one single integer. That is a huge amount of memory. And arbitrary precision. So this is how things work in C. Again, pure integers. You cannot exceed it beyond certain limit. No overflow. But in Python, there is no overflow. Python dynamically allocates more memory. So what the size will do? It stores how many internal digits are needed, sign information, and size of the number. So internally, Python store integers at 2 to the power 30 chunks. That's what I was saying, that it would be 30 bits. Why it's 2 to the power 30? Because it could be 1 or 0. So each of these 30 could either be 2, 0 or 1. That's why it's 2 to the power 30. Meaning a very large number is stored as an array of 30-bit blocks. Now, how many blocks are being used? And the size field tells you how many blocks are being used, and that's why it's 8 bytes. Number of blocks and sign information, and stored as an 8-bit signed integer. Why this matter? Python integers are flexible. Now, this is of course very good from the Python perspective because it's dynamic memory allocation, right? And but when you do it for individual for complex mathematical computation, it is actually acting as an overhead and not a good thing. Okay, so that's what is something that we are trying to explain here. Okay, and now comes the last thing, the actual integer value. So now here it would take 4 bytes for small ints. So let's consider that the integer is small. Okay. So this is actual data storage where the integer is being stored. It fits in a 30-bit chunk. So if it's a small integer, it fits in 30-bit chunk. So only 4 bytes needed for the value. But remember, this is inside a Python object. Okay, so this is not just an integer. So we are storing that integer inside a Python object. Okay, and the total size. So how many things did we discuss? Uh, the reference counter, the what do we say, type pointer, size field, and the fourth one is the integer value. So for these 888 bytes, which is 24 bytes, and 4 bytes for this, that's adding up to 28 bytes. So to store one single integer in a list, in a Python list, it's taking 28 bytes. Can you even imagine? 28 bytes of memory. That is huge amount of memory, you know. So just try to understand how much of an overhead it's adding up, you know. So a rounded total limit usually 28 or 32 bytes. So minimum it's 28. If it's an again if it's an 8 bytes of integer value or that 64 bits, then we would again have 8 times 4, which is 32 bytes of memory for one single Python object. 32, 32, 32. How many objects you are declaring inside the what do we say, Python array or list, plus the size of the list, which is in itself a Python object. So this is how it actually is adding an offset, or what do we say, this is how it's making it very 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 hard for the mathematical calculations to happen, because it's going to take a lot of memory, so let me just draw one more thing here. which should make things very clear and easy for all of us. So where is it? I'm not able to find that thing, what I'm looking for. Yeah, let's do this thing. Sorry. Let me pull this container directly over here, or let's move it here. Oops, where is it now? Uh, okay, okay, let's keep it here. Text field. I want four text fields. Let's move this above. Copy this. Copy this again. Okay, cool. Move it a little bit down. Make it 18. So the first thing is reference count. Second thing is type pointer. It's 18. Third thing is size filled. It's again 18. And the last one, no, wait a minute. I'm just copying this and then pasting it over here. Integer value. This is specifically for any number or many integer that is being stored, or any integer which is a Python object inside the memory. Okay, so I want this to be pointed out. Sorry for that. Let's move this thing first of all here, so that it makes it easier for us to understand. So it would have for this, as well as it will have uh, we would have this thing for this. So these, both of these are Python objects, and each of these object would have these things in their life cycles: reference count, type pointer, size field, integer value. And depending upon what integer you are using, a 32-bit or a 64-bit, the total memory that this single Python object would take is 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 approximately equal to 28 bytes to 32 bytes, depending upon how much of uh, do you know the what is the integer value, whether it's a uh, 32 bits or 64 bits. So this is the whole picture about how, or this is the whole picture how different integers are stored in lists, and why is it so memory expensive to store different integers in lists. Now let's look at what NumPy is doing. So now we saw that NumPy stores this as a contiguous block of memory with not each element as a Python object, but rather raw memory. Inside a raw memory as scalars or whatever integers we have. Now each element 4 bytes only, because this is an integer. It's a 4 bytes integer. 2 is a 4 bytes integer. 3 is a 4 bytes integer. For like all of them, because we have specified that it's a int 32. So each of these integer would take only 4 bytes. But in list, each of them was either taking 28 bytes or 32 bytes. Here it's only taking 4 bytes. Try to understand the difference. No reference. So these four things are not adding as an offset to to the entire to the entire array. So did you see? Just I mean, uh, just understand that declaring this and declaring this has how much difference behind the scenes. Uh, I mean, just imagine that when you declare a list, how much things are happening under the hood, and when you are declaring a NumPy array, what other different things are happening. So it's that much of a difference, and you can imagine how much of an offset the lists are actually adding for the memory or for any of the calculations that you are performing on them. Okay, so Python list of 1 million integers, 28 MBs of data. So these are approximate calculations. And the real insight is when you create this, memory looks like this. Each integer is a full object. When you create this, memory looks like this. No objects, just numbers. So why this matters for AI? Now, what is the relevance of this with AI? Millions of multiplications. So if I'm doing this with pure Python lists, it would include millions of memory writings and memory, reading, etc., etc. Billions of additions, and this is actually adding an overhead and doing nothing. And NumPy removes all this. So now, what we would do is, so this is a code. Let's try to, uh, you know, try to actually set or understand what is going on here. So first of all, let's declare a list. Uh, we have already imported NumPy as NP, right? So let's declare a library called as import sys, which gives you a system level access to you. Then let's declare a list. Let's name it as. I mean, naming variables is a very hard thing in programming. So let's write this new list. Let's equal this to something like 1, comma 2, comma 3, comma 4. Okay. Now print. Let's print the what can we print first? We can print the size of each element first. Size of each element. This would be equal to sys dot size of, let's access the first element of the list, uh, and because all of these are integers, the Python objects would be same, and that's why it's same. So first let's try to print this much. Has no, so sorry, it's not size, it's size of, if I'm not wrong, dot let me just check what it actually is. Mm, Let's go from here. It's get size of. I'm so sorry for that. Uh, mm, System dot get size of. Okay, cool. So got it correct. It's 20, and this is raw memory or raw bytes. So these many bytes. Okay. So it's 28 bytes for each element. And now, if I want to get the size of memory or the memory size of this entire thing, then I would just write uh, print f, not like this, size of all the elements and the list would be equal to, first of all, I'll just uh, get this get the size of get the size of the entire list plus I will add into this. So let me just do one thing. Or let's do one thing. Let's do this thing separately. And total size, let's go size would equal to this size plus how much element. So let's multiply this as the length of this new list, that much, with the system dot size get size of the individual element. So for example, I will just write new underscore list and the first element. Okay, and then I will print directly this variable here to make much readable these many bytes. Cool. And if we want, we can also print only the size of list. This is something which we could not say about. You can write system. So first of all, let me say this as an string. A string and the system dot get size of, and here sorry, size of, right, the my list, my new list, new display list, this much bytes printed. Cool. So you can see that this list is 88 bytes and each of the element is 28 bytes. So 28 into 4 is how much? 12. 112 plus 88 comes out to be 200 bytes. So this one single list is taking 200 bytes of memory. And now actually let's go on to what does NumPy have us to give. You know, so after this, let's have a NumPy array. Let's declare an p dot array and have it as 1 comma 2 comma 3 comma 4, and let's also have its data type to be equal to np dot int 32, and let's run at least this much first. Okay, it ran properly. Now we directly have methods in NumPy, and to print the number of bytes that are used, we will write the byte memory taken by the, what do we say, the NumPy array. NumPy array is nothing but np underscore array dot nbytes bytes. Let's try to print this out, and it's like these many bytes. Cool. You can say it's 16. Why is it 16? Because this, so every element of this array is a 4 bytes of integer, and 4 bytes with 4 numbers, 4 fours are 16. So it's taking in 14 bytes of memory uh, to store this NumPy array. So can you even imagine where is 200 and where is 16? So this much is the memory gap when we have a simple Python list and when we have a NumPy array actually. So this is why you really need tools in AI which would help you into doing mathematical calculations very easily. So I think you understood this thing. Now let's move ahead and check what do we have next. We completed till this. So here the code is more organized to look it more pretty, and that I'll provide you guys this thing. And now speed. Now speed is critical for AI Python list. What actually happens is whenever you try to perform any mathematical calculation on any of the Python list, or then that mathematical operation happens element wise. But when you go into NumPy, there is a concept of vectorization, and you can imagine like there is a vector and that is stored in a block of memory. There is another vector that is stored in a block of memory, and when I add these two, then it would be directly added. It would be added blockwise and not element wise. So that makes calculations in NumPy faster. So we would again have a piece of code that would explain all these things. So first import this time module, because we need to do time comparisons between how much time is it taking to do the calculations. And as we declared above, we will use 1 million thing again. So this is nothing but 1 million. And let's declare a list, that is, name it as a list, which is nothing but a list of a range of numbers of n. And then we would again have a list similar to this, but we will call it a B list. Okay. Now after this, let's have a Python now NumPy array. So let's write NumPy underscore array underscore one, which would be equal to np dot a range n. I'm not sure whether it's correct or not. Yeah, I think it's like this only. Let's first try to run this thing. Yeah, it is correct. And NumPy underscore array underscore 2 is equal to np dot range n again. Okay, so we have So what we have done is we have two lists of same numbers and two numpy arrays of same numbers. And what we will do is we'll try to do some calculations on this. Maybe add these two lists and add these two numpy arrays and then check which of them is actually performing better, like which of them takes less amount of time to complete. So what we can do is let's start the time. So t0 underscore you can write for maybe the list is equal to time dot per underscore. I think what is that function? I don't remember the exact function name. Counter. Okay. COUNTER. So these are the. This is one of them. So we are just starting the counting thing here. Now, what is this perf counter? So this is a very highly, precise counter which is used to, measure the differences, the time differences between calculations which are highly precise. So it gives you precision up to a lot more decimal places. Okay, and then what we would perform is we would try to perform the sum of the arrays or lists, sum of the lists as ts, which would be equal to nothing but a of, I can write it something like this, copy from here, I of this plus copy this, I of this, make this b, mm, for I in range of n. So what we are doing is we are performing element wise addition of these two lists. So it would iterate over, million numbers, and it would try to access element to element and try to add all of them. And after this gets performed, we would try to again call this same function, that is this function, and the total underscore time underscore list would be equal to uh, this minus this, and we would try to we need to perform this thing first. So we'll do this and multiply this thing with 1000. So this converts this time into milliseconds. Okay, and you can then print out that the time taken to perform addition on the lists is uh, copy this thing, these many milliseconds. Okay, I'm so sorry for this. I just missed a P here. Okay, so it is somewhere around 32.83 milliseconds. Now we would try to calculate the same thing for the numpy arrays. Just copy this down, and these two things would remain the same. And here what would happen is we would just add this thing similar to as we do addition on paper, and then you can write this as numpy. Similarly, this also as numpy. Just see the difference. So This is the power of Numpy again. So here the time taken is way more lesser than the time taken uh, by it.
perform addition on, you know, the direct direct Python lists. So I think that this much is enough for the first video. I mean, there is a lot more in depth understanding about what goes beyond NumPy, and we will discuss a lot of more things. But for today, this much is enough. And I would say, if you like my video, please share, subscribe, comment, and like this YouTube channel. And believe me, we together are going to learn a lot of things. Thank you, guys.